All right. So this problem is similar to the last one that we did. It's the exact same thing, except instead of a CSTR, we're going to make this a plug flow reactor, which is like a pipe that moves all in one continuous motion, and the point of concentration, or the concentration at any point, does not change with time, but the concentration changes throughout the entire reactor. So that's what we're gonna see here. And I have all the housekeeping stuff right here, and then I have all the same parameters because they're all the same. There's only 2 parameters that are different this time. They're the same thing, but we have to treat the plug flow reactor like it's a series of CSTRs. So this is gonna be all the same equations are the same, just with a whole bunch of sums. So to start, we need to set a number of reactors equal to 15. And then we need CAO. CAO is equal to, we make this into a full, which is similar to an array, but it just shapes it for you. So this is going to be a full of N, and then the concentration in is going to be 0.5. And then T0 is going to also be with the shape of N, and it is 350, because everything starts out at 350. And I did it again, didn't I? Alright, let's just make sure that's right. Yep, that's what we wanted it to be. Yay. Alright, now we get to make an equation. So we're going to define, and this is just a discrete function, and this will just be define PFR, that's the type of reactor, with respect to time, and a vector. CA is going to be equal to this vector, but we're going to make this vector 2 parts. One part's going to be temperature, one part's going to be concentration. So we've got V, I think I need brackets. So V, and it's going to be this colon and N, which means it's going to be that part. And then T is going to be equal to V, but with that. So with that, we've set up half of a vector, or 2 halves of a vector, and now we can have our dCA, which will be the same as it was last time, except we got to put in some more variables. And actually, we have to define dCA twice, because we got to define it for the first tank differently than the second tank. So dCA is equal to Q times CA in minus CA, the first term. What? Okay. And of course you don't want to work. Over V minus 0 CA0. No. Okay, 0 times CA0. There we go. Otherwise. You know what, just for simplicity, I'm not even going to capitalize this. Alright, so we got that. We need to define our T0. Actually, I need to have this as dCA0. So this can be dt0 and this will be equal to that Q in times times T in minus T0 over volume. Did I capitalize? Yes, I did. All right. Minus UA times, actually this needs to be in brackets first, T in minus T, and then this is going to be the 0 again because we want the first term, minus the HR. This one I need some more parentheses. NHR, K0, CA0 divided by rho CP. No, I gave you more. And then copy these. Well, of course I did no copyright. DCA DT. Replace this with 1. Replace this with the last thing of the series, which we'll call -1. Actually, I think you need to be there. Then you need to be there. And then your and then these two terms should be the same. And then you need to be -1. I think I've messed this up a little bit. Actually, this needs to be the cooling water because we're focusing on that. We're not focusing on just the straight temperatures. That's what the UA term is for. Okay, and I did neglect the over rho V CP for both of these. And then I get a return a concatenation yeah, I spelled it right. This is set up like an array, and then this R thing, concatenate is putting them together. And then this R thing is going to separate them. It's R underscore. Yep, it's going to be row wise. And then we need it to be DCA O and DCA. We want those two separated. And then we want another row-wise separation dTO and dt. I just can't get this right, can I? Alright. I think that's all we need. And then we need resolution. Result is equal to solve IVP, as we've done many times before, with our plug flow reactor. From T to, I didn't set a time for this. T is equal to, say, how long are we supposed to run this for? Come on, Carlos. He does not say. So I'm going to assume around the ballpark of 5 minutes. No, I know I haven't finished it, but I need it from 0 to T. That's the time frame. The Y0, I don't think we care about. Actually, wait. Y0 will be. And then we want CA and TO. That's the right way you do it. Method is dough, and then dense output. And I messed it up. Int is not callable. I forgot. Still not good. Oh, now it's DCA. Great. Oh, I didn't define K. Duh. Just sitting here using K. K equals K0 times e to the PR over T. Of course I did. Now I'm going to guess some of these aren't K0s, so I need to check my equations again and make sure I got it right. Alright, I believe I found some other mistakes too. Like this is supposed to be the first term, and then subsequently, no, I already fixed that one down there. Because it wouldn't make sense to have this be T and that be T1, T the last, rather. But this needs to be, this needs to be the first term of K, which there isn't one, it's just K. It's just the first term of CAO. So, we get that. Still doesn't want to be right. Oh, now concatenate's wrong. Yay! Let's see, maybe these parentheses are screwing with it. Just the Google didn't use these. Oh, now it works. Alright, and now we have to plot these up. I just checked over that video and I realized two things. One, the most important one is that this camera right here that I'm waving to was frozen the whole time because OBS is mean to me. So that doesn't deter too much from the video, but yeah. that was not a good thing to discover. And second, I forgot to divide the UA and the volumes on this by N. So that would have just been wrong. So we got to divide that by N. That means that I have to put N up here. And then I gotta divide the volume by 15. It's a good N, in case I wanted more. Okay, I got that done again. I don't know what that means. I hope that's not detrimental to anything. But oh well if it is. Alright. So to do this, I'm going to need a time plot of the number of n's. So I'm going to call it n and a t-plot, which is going to be equal to 501 because we want it to actually be 500, but Python has 0 as its first number, so we got to treat it with respect. Never thought I'd be saying that about a computer. And then we need to make a time plot, and that's going to be numpy in space, and it'll be from 0 to t with the number of those things, so 501 spaces. And then we'll need CA and T both to be equal to the result of the last thing, the solution from there, and we want that to be with respect to the time plot. And we actually want to reshape this to be 2 rows. I think it'll be 2 rows, n long, and I need to make it NT plot. All right. No. And then, so this will be actually pretty easy. I just have to make a figure, and I have to set it equal to, make subplots, of course. And then I want rows equal to 1, columns equal to 2. And then actually to plot 15 of these for I in range n. I'm not completely confident that will work, but no, add scatter. Alright, and then x is equal to time plot, y is equal to CA, just with I, and then capture everything there in the row, and then we want to name it and then I'm going to call that I, because we want the i's to carry over. and then copy that, change everything to Fig2, change this to T, change this to T, and then I think, what did I do? Oh, didn't even have the W. We're still wrong. Oh. I made the same mistake twice and just copied it willingly. Why didn't you plot? Well, I found that immediately. Didn't even run the first thing, so how could it do anything? Okay, it still doesn't work. Yay. I literally could not make more obvious mistakes by having them in the same thing. It still is not plotting, and I don't understand what's wrong. So I didn't find the actual thing that's preventing me from plotting, but I did realize this is supposed to be negative, so I fixed that and fixed the overflow warning here, because apparently even the positive number would be detrimental. Okay, so as I suspected, this having this within the having that within the oh, you've got to be kidding me. I actually could probably just, oh boy, let's try this. No, you still don't want to work. There we go. Okay, I could have just shortened that the entire time. I didn't need to make two. But yeah, I had to update the layout. Because I sat here and I put add scatter again afterwards, and it worked. So I'm not going to look a gift horse in the mouth. Alright, so these are the temperature and concentration profiles. So currently, as we can see, this is the concentration in each goes up and then goes to a steady state, but after a certain point they're all the same concentration. So they initially go down because they're getting used, because they're leaving the reactor at the end of it, and there's no new stuff coming in, and our new concentration is closer to 1 coming into the first CSTR. And then our temperature is going down because we have that cooling water running concurrent to the plug flow reactor, and it cools it down more as you go by. So T1, or rather, which one are you? Man, this is atrocious, the way these names are, but oh well. So I'm guessing this is T14 and this is T0, yeah. And it makes sense, it get cooler as you go on. There might be another set of graphs that I have to do for this, but I don't know. I do think this is going to be enough for what I need, because it still does show how each CSTR reacts over time. So we can see how each one goes. The bottom, like, it looks like everything but the first two are going to go down significantly in concentration and then eventually steady out. So then there's a big jump in temperature between time 2 and time 3 and time 4, something like that. And there's a big jump in temperatures here. I don't know why. But we can change our cooling water to be 310. Let's just go 310. And you'll see the concentrations. Whoa. Didn't even know that was possible. Oh, okay. I guess with exothermic reactions, it's a really problematic thing, because that would most definitely blow up and be a runaway reaction. Not that that would matter, because these all went into the negatives pretty quickly, I think only CSTR 1 is maintaining barely 0. Oh! Me being a drama queen. Okay, so it doesn't really affect it that much to change the cooling water by 10 degrees. But it does change it a whole hell of a lot to be 1,000 degrees more. Yeah, it doesn't really change it, but there's less of a jump in temperature when you have a lower cooling water. So let's actually just do some more drastic changes. All the concentrations are pretty much equal because there's no reaction, because, well, there is a reaction, and it's going a lot slower because it's a lot cooler. But you would think it being exothermic, maybe I didn't do the calculation just right, and this is actually supposed to be negative. Okay, so it is, I did it again, didn't I? Man, I gotta be more careful. Okay, this looks more like an exotherm than the other thing. So I might have messed this up royally. Yep, I did. You're supposed to be plus. And you are supposed to be negative. And you're supposed to be 350. Nope, still not normal. Yay. I had some errors here with the this. I had this as -1. This is supposed to be +1. I had these as 0. They're supposed to be 1. It's still wrong, and now it's even more wrong, going off into like 60 trillion. I did it again. Yeah, boy. These were both 0 too. And that was the only thing that was wrong, because now this is right. And these concentrations are supposed to raise sharply because they're coming in at 1, but then they react and they all go to 0 pretty quickly. And I can shorten the time if I wanted to from 5 minutes down, but I'm not gonna. And then these temperatures go up because the cooling water acts less as it goes further in, but it acts a lot more because you're getting that fresh cold water in from the concurrent system. I would assume it's concurrent. If it was co-current, that wouldn't make any sense. But yeah, this concentration's getting obliterated pretty close, pretty early on, because it's all getting reacted. It's all going to just about 0. There's still slight little bits of A left because you can never truly get it out. But yeah, alright, so this is what happens when you change a CSTR to a plug flow reactor. Alright.